thank everybody for being here tonight. We have two presentations tonight. One is the Freshman Imaging Project, and the other is the Photoscience Senior Capstone Project. I'm Karen Braun. I'm the Associate Director for the Center for Imaging Science, and myself and Dr. Bob Kremens back there in the corner and Dr. Flip Phillips are the instructors for this course. And we have a great group of students. They'll tell you a little about themselves, but it's a mix of imaging science and motion picture science students. We have a small selection tonight, but we have 17 kids in the class. These are the ones that could be here tonight, and they sort of rotate through who does the presentations and things like that. So,
hello everyone, thank you again for having us here. We're just a few members of the Photoscience Capstone of 2025. I'm Paige Wright.
Hello, I'm Charlie Lerch.
I'm Charlie Gray.
So today we're just going to be talking to you a little bit about our presentation. A little bit of overview. For our project, we have been tasked with building an all-sky cloud imager. Ever since the DEERS group in 1999 started, they have been giving thermal infrared information to NASA to help calibrate Landsat thermal sensors. The most recent Landsat satellite was Landsat 9 and was launched in 2021 by NASA. Our system was constructed to provide critical information for the DEERS group to use to help to assist in the calibration of Landsat 9. Our main objective of the system is to provide cloud percentage coverage over time. A little bit of our general design. Our system was designed to be lightweight, easy to use, be low cost, have a wide field of view. We are specifically told to have somewhere as close to as 180-degree field of view as possible, be able to collect basic weather information, and last to up to roughly 8 hours of data or more, and be usable to 3 to 5 years with minimum requirements of maintenance. For our cost, we ended up being able to build one unit for just $760. This is in stark contrast to other all-sky imagers that are out on the market that can be $10,000 to more. As you're looking at the pie chart, you can see that we allocated used most of our money to our housing, but that also does include the prototypes that we made with our housing. The next was our battery and power, as well as our processor, our circuitry. Our camera and lens was actually the second to least item that we spent the money on. A little bit of our hardware selections. For our sensor, we ended up going with the Raspberry Pi high-quality sensor. The mount for the lenses provided us a bit more flexibility with when it came to our selection of lenses. Speaking of, we ended up going with a lens that had a 195-degree field of view, so we did surpass that requirement that our customer gave us. And it had an f of 2.0 aperture. For our processor, we ended up going with the Raspberry Pi. It provided us with 8 gigs of SD RAM, as well as a 40-pin GPIO header and 4 USB ports. For our Anchor Prime battery pack, we went with it because it had a lifespan of about 2 to 3 years. We actually calculated with our system that you could use it for about 12 to 15 hours specifically. We also had a touch screen display, which went a bit more into the ease of use, which is a 7-inch display, and the bezel allowed for an easier sealing. We also went with something that had an anti-glare coating, so since it's going to be out in the sun, we're not going to have any glare on our screen. It'll be easier to see. For our weather station, we used the Arduino Nano. It was compatible with our Raspberry Pi GPIO pin, and this allowed the Pi to focus on collecting the images while the Arduino focused on getting our weather data. We also had to get a level shifter to help with regulating the voltage between each of the processors. We also went with a pressure sensor that allowed us to calculate between 0 to 25 psi, and our temperature and humidity sensor allowed us to get an accuracy of plus or minus 2% for relative humidity and plus or minus 0.5 Celsius. The sensor also had a mesh casing that allowed it to be waterproof. Moving into our housing design, which you can see in front of you, this is a bit of an X-ray view from the AutoCAD application. You can see on the inside that we had these little mounting points to help with holding our hardware components. And then this is just a little view of how the two pieces, the main compartment and then the lid, interact and connect. This is a little view of our final design. It has been printed in 3D PLA plastic. It holds the internal components securely, like how I mentioned with the mounting parts. And we also have an optional hydrophilic dome that is mounted at about 2 degrees, which allows for moisture and any water to roll right off. It is also detachable, foldable. We have a hood here that allows you to protect the screen and reduce glare. There's also a compass on the top of the hood that allows for easier orientation. On the back, this is where we have our weather station and fan sensors. This number 2 is where we have our fan, and then number 1 is where our weather sensors are. And this allows for us to have airflow to flow between each gap nice and freely.
So on the software side of things, we put together this little flow chart to just help go through a little bit what we're doing more. Visually, it's easier to follow, but upon startup, the user is prompted for a couple of inputs. We'll discuss that more later. Then after going into that, we go into our main loop where we go into our image capture, we collect our weather data, we record all of our data, and then output all of our assemblies as necessary. In the image capture side of things, we start off by checking if the sun is in the image. We then equalize all of our images. We go into our cloud detection algorithm. Lastly, we make a couple of our calculations and then output the cloud movement. So for user interface and like camera control stuff, we have the user at startup put in the capture duration that they want, or they can set it to until the system dies functionally. A capture interval, so we have a minimum capture interval of about 5 seconds, and then that can be as long as you need it to be. We also have an image cropping function, so if you have a building or trees or something close enough to affect your actual data collection, then we can crop that out for you. After entering these, you'd hit start, and the system will start collecting all of the data we need, but it will prompt you to have the system face north. This allows us to actually determine which direction the clouds are moving. So this is what our actual user interface looks like. So when you open it up, you have this first large image here in the center. You have a live view of what the camera actually sees. You have 2 options for close the camera or to crop your image. You have the option for changing the duration that you want to capture. And then you also have a progress bar. So you can also go to our settings option, and that gives you a little bit more in-depth information. So that's where you can change how often you want your images to capture. Our system outputs a time lapse as well, so you can change the frame rate of that, and then it will also tell you which of our sensors from the weather station are reading incorrectly. So this is a little bit more close up of that so you guys can see it better. For instance, this is what it would look like if cropped out. And then the graph on the left there is the cropped in image, right?
Yeah, this is how you crop it.
Okay. Is the actual like what it looks like when you're cropping the image. So for our actual main loop of stuff, we do our detection, calculation, and movement here. For our actual sun detection part of this, we just do an image moment. So we're checking for the weight of the center, like blown out pixels. So we actually threshold that for being over 100 to make sure that we're only taking into account where the sun is likely to be and not where there's a bright spot in clouds, for instance. So this actually just gives you XY coordinates, and then we put a big circle just over where the sun is and then remove that from our actual calculation. This does introduce a little bit of error, but we determine it's a little under 1%. This mask ends up getting used quite a bit later as we remove it from all of our other calculations as well. So for the detection methods that we use for the clouds, we have 5 different methods. 4 of them have to all agree for us to have the actual final mask show that as being a cloud. We chose these because several of them are very different, or because we're trying to decorrelate things as much as possible. So for instance, the Otsu method up here is a essentially 50-50 threshold that masks over and under your median value. We change that a little bit to get slightly better results. we take a red-blue threshold, a red-green threshold, and then a green-blue threshold. All of these channels have been equalized prior to this happening. And then the sun mask gets divided out or removed out as necessary. And lastly, we do a skimmage binary pattern. This is a textural analysis of the clouds. It is by far the most different method that we use, but it is also almost entirely uncorrelated from the others, which is kind of the benefit of it. So lastly, we're asked to actually weight the images, since as we're going out across the distance of the sensor, we're having more and more area accounted for each pixel. So this ended up being a geometric weight mask that Eon from upstairs asked us to do for him. So this actually is what it ends up looking like, with center values being reduced to under a value of 1 and values on the edge being approximately 2. It varies a little bit. And then this is what the actual mask looks like, with the blue being entirely masked out later on. This just entirely is accounting for differences in spatial relationships. So calculating the actual final cloud coverage, we remove each of our masks as necessary. We then determine what the actual potential pixel max would be, and then just make that a simple percentage there after applying the weighted mask there. So we end up graphing this data as individual data points over time, and then that allows us to visualize the cloud movement, the cloud direction of movement, and the cloud percentage over time. So for the cloud movement side of things, we just do an optical flow function. It's by far the easiest and works perfectly well for our needs. And we're just looking at the difference between 2 points every 30 seconds. It gives us a really good output. Each frame ends up getting segmented, as we discussed in the previous slides, same segmentation methods. And then we determine cardinal directions and intermediate directions. And that allows us to, within about a 22-degree field, tell you where north, northeast, east, for instance, is. So I hit the wrong button. So for the weather data, we actually collect a couple of data points and we calculate a couple. So we collect our temperature, humidity, and pressure, and then we end up from that calculating our dew point depression, and a cloud ceiling estimate. The dew point depression is a metric that gives us some estimate of what we expect cloud coverage to be. So for instance, if it mismatches too much, we would know there's an issue. So for the actual testing side of things, a little bit of a disclaimer for our ground truth here is that we didn't determine a ground truth for our device. We determined it from other data sets that we were able to access. This ended up functionally being this SwimSeg data set. It was made by a group in Singapore alongside of a bunch of cloud and climate scientists. So it is a very good data set for us. We do have to do a couple things to make sure that is accurate for our system and how we were testing that. So we ended up fisheyeing these, checking what we knew the values of clouds to be, because it gave us these images and a segmented image, and comparing that with what we collected with our methods. We ended up determining that our system was about a plus or minus 10% accuracy, and that was well within the threshold that we were asked to provide.
Now moving on to the outputs and results of our system. We output 3 main data types: the JPEGs of the images themselves, a CSV file that contains all of our cloud movement, detection, and weather data, and the plots that are generated from that CSV file. In the user interface, as you saw, the user gets to select which of these plots they want to be made by the system itself as soon as it finishes running. This is just a survey of how our system performs under different weather conditions. I think the system performs very well. The sun mask is incredibly competent. The things we struggle with most are glare from the sun, as you can see in that image there, and buildings. buildings is why we have that cropping function. This is our CSV file. Looks just like a CSV file. It's important to note we have 10 possible plots to make, which is why we have that option to not make them all immediately. Every value is calculated just as the system is running, so there's not a huge lag when you finish. This is a sample of one of those plots. This is of coverage over time. This is over a 2-hour span. Very neat. And this is a better visualization of what our optical flow algorithm gives us. You can see the images on the right there give us, that's how the image comes out. All these vectors map to all the pixel areas where there's movement. We then average the direction and magnitude of those vectors to give us the data that we write to our CSV file and then plot. This is an option for one of the graphs we can make with direction over time. This is an area of contention right now, how exactly we want to plot direction over time. This is just one option that I disagree with, but it came out very, very neatly, so we put it in. And then final notes. There's a lot of future work that can be done on this system with Ian or his legion of grad students. First of all, we could add a GPS or magnetometer to better figure out exactly where north is for cloud movement direction instead of relying on the user's input. We could expand the amount of sensors on our Arduino to have more weather data pulled in. We could adapt the system for nighttime capture, which would be hugely beneficial, but it's a lot of code and hardware to swap. We could reprint the system in resin, which is obviously more expensive, but also more durable, more weather and UV resistant. And we could also go through and validate ground truth better. Any questions?
Oh, very interesting. Good work here. And I saw an earlier version of this, so you guys have obviously made a lot of progress. So the results you showed were from an archive data set. Have you actually taken any data with this?
Yes.
Does it work?
Yeah.
Yep.
Yeah.
So this is all.
This is from the system itself.
Yeah.
Oh, okay. Okay.
I also, by full disclosure, got a chance to see this many months ago, last winter, and I'm very impressed with the progress and the stuff you guys done. I should ask more questions. First, I gotta say, I was really impressed with the Jacobian weighting of it instead of de-warping the image. That was just very expensive. A simple multiply is so much cheaper. That was brilliant.
That was definitely Ian's idea. It was something that we had discussed as being important and something that would need to be accounted for. The things that we had discussed as being options were to either look at the center, say we're really confident, like 90% confident that our center area is correct, say that's for the whole scene. He ended up suggesting this, which I think we all kind of agree to be a slightly better option. There was a little bit of contention, like with the plots, whether or not we weight the center or the edges heavier based on confidence or based on our actual area being covered.
Did you end up using any HDR techniques, or are you doing just single captures?
We're just doing single captures right now. That definitely would solve some of the flare issues that we have. Although with it being such a high field of view lens, that's just something that's not going to be entirely resolved. So that definitely is something that we had discussed and ended up not implementing, partially due to the constraint of it already taking about 3 or 4 seconds to process everything. So we didn't want to go too high on that interval.
In your field testing so far, what have you discovered as challenges you want to change about your enclosure environment, rain, moisture, dew, that kind of stuff?
Kevin, do you want to answer that?
Sorry, I'm distracted by saving the poster. What was the question?
Your experience of using it in the environment. What have you learned about the enclosure and your design so far with regards to how it sheds water, dew, moisture, fogging in for the inside? Any things come up with?
With the design of the physical system, so far there haven't been any major issues. I would say our biggest concern would be with the PLA and UV right now. And so we do plan on giving it like a true clear coat that's UV resistant. But I would say that's our biggest concern at the moment. We haven't really had moisture problems or anything. And we did have at first the like permanent optical window that was fixed on top. Now it's actually a twist on option. So if it's a nice sunny day, you just don't have to deal with that thing at all. Oh, well, we're going to pretend like that didn't happen. But you just don't have to deal with that at all. And it solved a lot of issues. But if there is like light rain or anything, you could put that optical window on. It does create a few problems of its own, but we're working through them.
And,
Okay.
go ahead.
I was just gonna add that, yeah, I don't believe they're gonna be using it mostly in like when it's raining or they're like high moisture areas anyways. So that was another reason we had the addition, like the optional twist on. We decided to do that. And then yeah, so far we just haven't really tested it in high like moisture areas, like times a day, like in the morning or anything like that. So yeah.
But I think it was also mainly because they made it somewhat clear it was never going to go out in pouring rain or anything.
You collect weather data. Is that just to augment the other data, or is it used as a predictor for some of the cloud segmentation?
So the dew point depression was originally supposed to be used as a metric for determining accuracy. That ended up not being really as good of a metric for determining that as we expected, and our algorithm did just fine already. But we were asked to collect some amount of weather data as well as, well, for instance, humidity is a huge predictor for cloud coverage. And so they did want to know, for instance, that temperature and humidity at this cloud coverage was what they were expecting to see when they pair this with, I guess we didn't discuss this, but I think we discussed this in presentation with you specifically. They originally wanted this to pair with a radiometer to check and validate Landsat data. So having at least a temperature and humidity option for collecting data here was really important, so that even without the radiometer, they knew what the temperature and humidity were and could, based off of their estimate, know if it was close or not. So it was important to have. It wasn't the like main focus of it.
Very good. And one last final question. I think you said your goal is 180-degree field of view. I think you said you have a 190-degree lens, but you can't mount a 190-degree lens in a flat surface. So how did you end up mounting the lens in a way that you can get as much, and how much field of view did you end up getting with
So we ended up masking into the center 3000 by 3000 pixel circle, which is about 164.5-degree field of view. And that the goal was to be somewhere between 150 and 170 after determining the weighting function. So we ended up obviously realizing that same thing. It doesn't perfectly fit the sensor that we have, so it does project on the top and bottom slightly over the width of the height of the sensor. So we do lose a little bit there. The amount that we actually crop out from our sensor only ends up being about 40 or 50 pixels. Yeah, 40 pixels. So we're getting essentially the maximum resolution and field of view that we can for this system without losing anything.
I lied, one more question. I thought of it while you were talking. I was listening to. So I saw that the flare from the sun and stuff is an issue. How much of that flare is from the optics in the lens itself, and how much is it from the cover glass that have AR coatings on it to prevent some of that that scatter?
So the images that we were showing didn't have the optical window on them.
Okay.
I don't know if we put in or if we had taken an image outside in the sun like that with the optical window on it. There are some small distortion issues around the edge when we have the optical window. You reach the actual threshold where you have total internal reflection before the edge. Very, very close to it though. And so you do get some amount of the internal rim here actually being seen, which is why we chose to make this black instead
Sure.
of, I think we originally printed it orange like the handles, and it washed out most of it. So
Oh yeah. So with the issue of having like a better ground truth, is there like a widely accepted definition of what a cloud is? Or is it, because I'd imagine like near the borders of a cloud you have I guess like your vapor density would change. So
So in short, like, no, it's not super consensus, or there's not a huge like consensus on it. That was one of the benefits of using this data set over ones that we had two that we tried to use for ground truth. The first one was one that was put together from different satellites collecting data from above where somebody took a photo of the sky. And I was like, this is the cloud coverage in like this photo. There were a bunch of issues with that. I'm sure you can imagine, since this was put together with actual climate researchers and meteorologists and everything, we chose to believe this was going to be the most accurate method. In reality, the option for determining a better ground truth ends up being that we would segment out and then train a model to determine what we say is a cloud instead of taking somebody else's truth for what is a cloud. And it does seem like it varies. For instance, one of the things that we discussed very early on was using IR and then looking at the absorption bands of water. And that probably would have given us a better understanding of what is a cloud or not, but at some point you're thresholding that anyways. So you might get slightly more accurate. You might also just have, you might have to then take into account it being so thin and it being like 30% water vapor, for instance. I don't really know. It wasn't something that we ever were able to put a really good definition on, or a really good, like, this is our metric.
Yeah, so a couple of comments. First, your cost 760, you know, it's a unit quantity. The usual, and comparing it to commercial, the usual cost to sale for small volume semi-custom electronics is 10 to 1. So that's an $8,000 box. That's if you sell some, right? So, you know, the non-recurring engineering costs are always going to eat you. You guys had what, 6 man years?
Yeah.
7 man years. So at $250K per man year with benefits, that's your NRE right there. So just for reality checks, because you know, I do the same thing. I make things for $200 and I give them to my researchers, but they really cost $12,000, you know, with my time. Second thing is, how did you correct the lens? Did you do like a cage, a geometric cage? Did you get?
So
how'd you find the distortion?
We don't do a distortion correction. We are doing a weighting function to correct to account for
pixel size for tombstoning, right?
Yeah. So realistically, it's probably larger than 2 times the area in the center. We didn't have a good method for determining that. Ian helped us make a lot of this since it was something that a lot of us weren't familiar with. So he gave us some of that code. We had some of that implementation issue review and came back to it. This is what we ended up with. But we actually don't end up doing a correction for distortion. We end up accounting for it by doing this weighting function.
Aerial weighting, right? Okay, should be good enough, right? You don't care where the.
Mine's quick. Oh, I just wanted to ask you guys what you would tell your September selves. Like, what did you learn just as working as a team, and maybe how you spent your time and things like that? Is there any advice you would give to, I don't know, like say a group of freshmen or just like yourselves when you started the project, or a group of faculty?
I guess the main thing would just be get as quickly but as efficiently as you can, get your organization down. That's going to be a lot of your base work. And then work from there and do a lot of testing too when need be.
I would say the thing I learned most was get on Eon's butt about having really good definitions for what he expects. Looking back at what we originally signed as like our contract with him was shockingly disappointing and ended up being like a here's a bunch of like concepts that would be great and not like a here's the metrics to meet. For instance, we had a very wishy-washy this is like what the accuracy needs to be for until maybe 2.5 months ago. Like it was a little rough.
Change majors as soon as possible. No, just try and learn the system that you're working on specifically as deeply as you can, because it seems like at first you'll just do one quick thing, but you're really going to need to understand it fully to be able to change it later, because everything's going to change later.
I think I would say more research and planning. I think we had a lot of research that kept continuing into into the process of actually building the system, which then we had to go back and change things. So I think a lot more research and planning would be better. So.
I would say like don't be afraid of like software or hardware you're not familiar with. Like we knew nothing about AutoCAD going into this, and we just were like, we're going to teach ourselves. It's fine, and it ended up being great. So, like, don't be afraid of like if you don't know a software, you can teach yourself. It's going to be great. You'll thank yourself in the end.
I remember the first time I ever had a computer video camera, which I got from you guys over in Elm Grove, I think. And so this was close to 30 years ago. And the first time I ever stuck it out the window and it's a time lapse, the thing that impressed me was how clouds at different levels were going different directions. And is that something that you guys have seen? Is that something that is a problem? You know, I mean, because your upper deck is going to be kind of obscured by your lower deck. And so I was just wondering about that.
Yeah, it's absolutely a problem. It ended up being something that we discussed and determined was very out of our ability to do, especially since so much of this is just looking directly up. You're obscured if anything's in front of you. And vice versa, like the satellite that this is supposed to be paired with is looking down. At some point, they're just looking at a layer of clouds over top of each other. And we kind of said we're fine with that being the case. But yeah, clouds do move very differently based on what deck or like layer they're in. This specific system ended up having the field of view defined for seeing approximately 5 kilometers at a 1 kilometer cloud height, which is a little lower than the median lower cloud deck.
I would like to know one fun fact about clouds from each of you.
Yeah, you got that.
They're poofy.
What?
I said they're poofy.
Okay, all right.
I hate clouds now.
And we hate drums.
Maybe.
I looked up the Latin name for clouds, but then I forgot it.
I think I have the opposite of Charlie. I think I appreciate clouds more.
This is a deeper question. No, I don't even. Yeah, I am a little sick of clouds. I'm not gonna lie. I kind of side with Charlie on this one.
Well, that's no longer a fun
But I also
fact.
think like give it. I know. Oh yeah, I kind of strayed from the. Okay, so what's a fun fact about clouds? Oh man, I think I still have to go with. I'm kind of sick of them. I'm so sorry.
I feel like I'm lacking a fun fact about clouds from one of you. A fun fact about drums, I do hate them. I can say that because it is unique from our group. It's not fun. Okay. All right. I don't know. My favorite drummer is Danny Carey.
Thank you.